So, hi, let's talk about space. So, let's see. So I will give you just a super brief introduction about RISE, so that you, if for the ones of you who don't know the organization that we are working for. So we are a collection of research institutes in Sweden, spread all over the territory. And we are a lot of people, over 3,000 people. That is mostly technical, I would say engineers and researchers, so in different areas, of which 41% is women, so it's great. And we have a lot of test beds and infrastructure that we work, like applying different projects and so on. But yes, let's give you also a brief introduction of what Earth observations are. So what kind of space are we talking about here? So as the word says, like we are looking at Earth from satellite. This can be done in two main ways. So we can either look at the light that comes from the sun and then bounces back from the Earth's surface and then gets detected from the receivers that we put on satellites. Or we can, from the satellite, send a signal that it might be radar, for instance, and then also, again, bounces off from the Earth's surface, and we recorded it with the sensors on board of the satellite. By studying a fairly large portion of the electromagnetic spectrum, so light that goes from ultraviolet light to infrared light, we are able to record a lot of information about soil, water, vegetation, land surface, water surface, and as you can tell, basically it's everything that is on Earth. So we can study a lot of different things if we look at this data. So indeed, depending on which satellite is your favorite, you can basically have use cases driven by the satellite that you're choosing, and this can be anything from energy to healthcare, weather, and so on. So it's very broad, the type of applications that you can have if you use Earth observation data. Also, this data is very abundant. Every day we get an enormous amount of data collected by, for instance, just the ESA, the European Space Agency missions. We have an incredible amount of data that we are collecting every day and every year. And so in Sweden, and specifically at RISE, together with Rymddatalabbet, we have built a platform that it's called Digital Earth Sweden, which has the goal of collecting the data from the Copernicus missions, so the ESA Copernicus missions, and collected on the Swedish territory, and hosted it at the ICE data centers for people to use. So this is an initiative that is mainly driven by the public authorities that are part of the Copernicus consortium in Sweden, but in principle it's open to everybody. So if you want to use this data, you just have to go to the platform, look for the area that you are interested in, and download the data. Also, we are interacting with all of these authorities and the people who are interested in working with this data to create data products that are more tailored to a specific downstream task that you want to apply them for, or studying them for. And so, if you're interested, just get in contact with us. Also, we have another initiative that is called the Swedish Space Data Lab. This one has been funded over the years since 2019 from the National Space Agency, but also by Vinnova and by SMHI, so the Swedish Meteorological and Hydrological Institute. And the scope of this initiative is to create a community of Earth observation users. So you see some of the organizations that are part at the moment at the third iteration of funding that we get. And the reason why we have a high interest in that is because we can gather together and use this, learn how to use this data, which is usually pretty complex, like together, like, and not in silos, so that we can better make use of our knowledge and share it with each other. As an example for this, that can be maybe interesting for this crowd, is the cloud optical mask model that we published last year. So the main goal with this was to, like, since we live in Sweden, and I think you all notice that it's cloudy most of the time. Yes. If there are clouds on visual images of Earth, it's a problem, of course, if you want to measure, for example, the status of the vegetation below. So we need to have a way to flag the data that are like cloudy over a certain threshold. So what we did here was to train a machine learning model on a synthetic data set produced by SMHI, where we could have a ground truth and see, like, okay, on this pixel there is this amount of cloud with this level of transparency. And then, so you can see in the first column, maybe I can point. So the first column here is the actual image shown in the 3 channels, RGB, so red, green, blue. In the second column, there is the cloud optical thickness prediction. So this is the value, the continuous value of the, from 0 to 1, let's say, of the transparency of the cloud. But then, of course, to simplify it, if we want to make a mask, we thresholded with 2 levels. So no cloud, thick clouds. And so you get these 3 levels of colors in the pictures. And this is the comparison between, like, on the ground truth that we had on a data set that was labeled by kappa zeta. And so this is to give you an idea of, and you can tell that, like, for instance, on this image, our model seemed to perform better than the labeled data from kappa zeta, because it recognized the thin clouds much better. And this is also what happens if we compare our predictions with the standard as a sync classification layer that does exactly the same thing. So our model performs a lot better. And because it's a lightweight model and performs this well, we also made the experiment of running it on a satellite. So that was a project run by AI Sweden, Unibap, and financed by Rymddatalabbet. And we sent, but it was under the umbrella of Space Data Lab. And we, so Unibap loaded our model on their hardware, and that was sent into space, and we tested the model there. And we were very satisfied with the performance, so we hope to redo the experiment with the same model, but like maybe upgraded with a better aerosol treatment and so on. So maybe next year I will tell you more about that. And then finally, I want to tell you about this great initiative that has been that has just started like last week, which is called ESA PhilLab Sweden. And it is an initiative that is driven by ESA so ESA wants to establish a PhilLab network in Europe. So each member state is going to hopefully open a PhilLab focused on a different area. The one in Sweden will be focused on AI, edge computing, and edge learning in space and for space. And what this initiative is about is essentially to distribute funding. We will issue an open call in the coming months, couple of months, and it's going to be around 900 kilo euros per year. So and we will be funding up to 3 projects. So please apply. Stay tuned on that. And now I will give the floor to Olof.
Thank you. Thank you so much. It's great to give just the second half of a talk because you're all just already warmed up. That's great. I will be talking about some of the downstream tasks that Chiara mentioned, and how we go about working with them at RISE and in the collaboration projects that we are working with. So firstly, this symbolic image of how we work with an AI model with these kinds of data and with geospatial data in general is that we have this box. It is a deep neural network. We don't need to show the details of it. And then we feed generally these layers of geospatial data, which could be different spectral aspects from the satellite readings. It can also be other kinds of data, such as altitude maps or even temperature readings. And then we train our models to use this and to generate some kind of output. Oftentimes the output is also some form of geographical format. And for those of you who are technically inclined, this is often done with a UNet or something similar, like a pixel-to-pixel model. For the applications that we solve with these technologies, that include land cover estimation, land change detection, cloud detection, and so on. One of these things that we have been working on together with the Swedish Environment Protection Agency, say that 10 times quickly, please. Is this one. We have made a map of a particular kind of wetlands in Sweden. We have annotated data from the Swedish Environmental Protection Agency, and this looks like this. So they go out and do field work in protected areas, and they annotate where they find this kind of a wetland, and then we can use that as a training data. We have both positive and negative examples because they give us that. But we have that only in the protected areas. And then we train our model and we can generalize it to the whole of Sweden. We can make this great map. And this is actually something that's being considered useful at the agency and which is in use. There is some artifacts along the border to Norway here, and it's because the input to the model is just masked out in the other side of the border. So we have some misclassifications there. It could have been removed from the map just. Otherwise, it seems to work actually really well. Wetlands are important for many different things. During our time of climate change, it's important for biodiversity and climate adaptation, being robust to downpour and droughts. It's also an important carbon sink. We've also done some work on stream flow forecasting, and the interesting thing here is that we have used this kind of model that I just mentioned to you, a pixel-to-pixel kind of model. Oh, 5 minutes. Okay, this will have to go quick. We get the supervision in measurement points where there are actual readings in the streams. But then we can generalize towards the whole area, and we produce this map of the stream. This can help understanding the dynamics of the flow with regards to elevation, with regards to the different kinds of soil, and so on. We've collaborated with SMHI with this, and we have also a collaboration starting with University of Sao Paulo, where they want to adapt this to their kind of data and try it out on that data. Another project that's just about to start now, or it started a couple of weeks ago, is our project, we call it Great to Green, which is in collaboration with Malmö stad and Uppsala kommun, municipality, and with Swedish University of Agriculture, where we're looking at gray areas. Those are the hard surfaces in an urban landscape. And we're training models to help the urban planning people to make good decisions on where to sort of transform these into gray areas. And this is something that's sort of politically decided that we need this in our cities to make them more robust to climate change, with flooding, with droughts, and also for shading and protecting people from heat islands. So that's really exciting. We'll use a multimodal approach. We'll feed in several different kind of geographical layers to the model, and we'll make the optimization based on that. We also do some more foundational work. This is work where we look at the different kinds of generalization properties of state-of-the-art models working on satellite data. In this case, it's land use classification, where the model predicts an area. It's a kind of a semantic segmentation task, and these different columns are when we perturb the input to the model in different levels. So to the left, we have the original input image. On the second row is the original prediction of the model. So it predicts it almost perfectly. Here we do some swapping of pixel order, and that is to see if the model reacts to different kind of texture in the map. We don't swap across maps, but we swap it within one semantic region. And with a little bit of swapping, that's fine. With a little more swapping, it starts to make mistakes. And if you swap all the pixels, so each pixel is actually swapped with probability 1, we get okay predictions in the edges of the mask, but not inside the mask. If we mask out the actual neighboring pixels and not do some swapping, it's still fine. But then the degradation goes much quicker. So the model uses the neighboring areas to make the actual prediction within the region. We did some more experiments. For example, grayscaling the image, that's fine. But pixel swapping it is not. Another work on generalization in these kinds of models. If you train the models using group DRO, some of you may know this kind of algorithm, you may get some benefit over standard empirical risk minimization, but invariant risk minimization doesn't really improve much here. Pre-training and data augmentation, that's the key here. That's what you need to do. Lastly, I just want to mention Climate AI Nordics, which is a Nordic network of researchers where we started just a few months ago, but we're now 140 people over the Nordic countries working on these kinds of tasks. If you're interested, go look at our webpage. There's more information. We do events, we do conferences, we have a newsletter, and so on. I also want to add that we are looking for 2 junior researchers in my lab. If anyone is interested in that, there will be an ad on our webpage soon. And with this said, thank you.
Yes.
Wonderful. Thank you so much for a super interesting and inspiring talk. We do have a couple of minutes now for questions as well, if we have any from the crowd. If you have, just raise your hand. Yeah, we can start right here.
Hello. Hi, my name is Selvin. And one of the things that surprises me is how much data, geospatial data, is available for free. But why isn't like AI spoken more about in this context? And rather, you know, where data is harder to get, there feels like more private focus is there.
I'm not sure.
Is it because it's complex? Because that's something that Chiara also talked about.
It is really used a lot in this application. So in that sense, I'm not sure I agree whether it's not spoken about, but perhaps it's not so widely spread,
yes,
and so visible.
I would say so. Because I mean, in principle, ESA has a lot of tenders and calls for applying AI to Earth observations. So in principle, it is something that it's an active field. But like I would say that maybe here in Sweden maybe we haven't seen that much, but I mean Olof is using them since. I mean, you're studying Earth observations and using it for your research since years.
Well, yeah.
So, I mean, I think it exists, but maybe it's a little bit less common that, like less commonly spoken about as like, you know, automotive or healthcare. Yeah.
Perhaps also it's not really targeted to the end user, but we're oftentimes the output of these things, those are used by authorities or policymakers, and then sort of the second-hand outputs, it's what's the broader public can react to, like the decisions made by policymakers, for example, which can be based on the outputs of these models.
Right, thank you so much. Someone else that wants to ask a question? Otherwise, I was quite interested in, like, given all of this observation of the Earth and all this data and all these insights that you're gathering, like, how is this? Who are you giving these insights to? Like, is it to politicians, to municipalities? Like, who is interested in this?
Should I start?
Yeah.
I think a lot of the time it is authorities, municipalities, policymakers, but there's also this field of sort of startup companies looking into this to this segment, sort of building their own products based on this data. Perhaps that's a long stretch, but sort of the one of the new startups that we started collaborating with just a week ago is they're called Beetle Sense. They're looking at bark beetles in the forest, and they want to make prediction algorithms and systems to remotely sense when there is an infestation going on. Sadly, I cannot say that this is an example where actual satellite data is going to work because they need to be closer. So they will be remotely sensing data from a drone.
Yeah, beetles from space. That would be very.
You can.
Okay, you can. Okay,
yes.
wow, amazing.
Yes.
You can detect it, but you detect it a little bit too late, I think.
Yeah.
Okay.
Yeah. I mean, it depends on what kind of resolution you're looking at. But like, yes, Skogsstyrelsen is doing the same thing as well with satellite data. So.
Cool.
And perhaps they have managed to do it early enough.
I don't know.
Right. Thank you so much for that. Give them a warm applause. And this is for you. Thank you so much for an inspiring talk. Thank you.
Thank you.